Swayam Prabha. Digital India. Educated India.
Hello everyone. In the previous class, we discussed about the rock slope stability and I derived a simple expression for the analysis of slope if it is undergoing the plane failure. We did not consider any tension crack in that analysis. So, what happens in plane failure? You have a discontinuity plane and a block is considered to slide along that single plane. Now, when we remove the material or during the process of the excavation, when the material is removed, there is a reduction in the lateral constraint, and because of that some tension crack may occur in the rock slope. It may occur on the slope face or above the crest of the slope. How to analyze such type of situation in case of the plane failure? This is what we are going to learn today. Excavated slopes, because of the removal of the material, displacement takes place in the horizontal direction and this results into the development of tension on a vertical plane. In case if there is insufficient tensile strength, this causes the occurrence of tension cracks. The moment this formation of tension crack takes place, slope may not be stable anymore. So, that is a very big concern for us, that the moment tension crack is formed, slope is not stable. Another cause towards the development of tension crack can be that rock slopes already have the vertical joints. Now, due to the lateral displacement, the separation between these vertical joints take place and this also causes the tension cracks. Tension crack develops up to about 75% of the height of the slope. As I mentioned that these may develop on slope face or upper surface of slope. So, let us say that this is what is, say, the slope. And say this is the plane of discontinuity along which the sliding of this block may occur. Now, this tension crack can happen here at the slope face or it can happen in the upper portion of the slope like this. So, depending upon where this tension crack is occurring, we need to carry out the analysis. What happens near the toe of the slope? That means this point, this is what is called as toe. So, what happens at this point? Here sufficient lateral strain, here the sufficient lateral restraint is available and therefore, the conditions which are required to cause the tension cracks, they do not develop and therefore, no tension crack occurs in this zone. So, the tension crack can occur either on the slope face or on the upper surface of the slope. The concern is we need to find out the minimum value of the factor of safety, because if we know that minimum value of factor of safety and if that minimum value is coming out to be more than 1, then we can say that the slope is stable. Now, for a critical depth of the tension crack, this factor of safety will be minimum. So, our aim in this analysis is going to be to find out the expression for this minimum value of the factor of safety. Now, take a look at this figure and try to understand the geometry. This is the slope, that is E, F, J. This portion is the slope, this portion. This is the discontinuity plane along which the sliding will take place, and the orientation of these two planes have been given by angle psi p for the discontinuity plane and angle psi f for the slope face. Height of the slope, that is from this level to this level, is given by h. You can see here the point G and K, and there is the occurrence of the tension crack. So, in this case I am considering that the tension crack is taking place in the upper surface of the slope, that is here, not on the slope face. So, this is the tension crack, and say the depth of the tension crack is Z. The width of this zone, that is Fj, is given by the dimension b. However, the distance of the tension crack from this crest of the slope is given by small letter b. The weight of this block, which is sliding along this discontinuity plane, is represented by W, whose component in the perpendicular and the parallel direction can be written as n equal to W cos psi p and t equal to W sin psi p respectively. Now, let us try to see how should we go about the analysis. So, from the previous class we take the expression for the factor of safety. So, we saw that this factor of safety, which we represented by F, can be written as C into A plus W cos of psi p tan of phi divided by W sin of psi p. This is nothing but the simple expression that we had in the earlier class, that is F was equal to Fr upon Fi. So, Fr was the resisting force and Fi was the force which was inducing the sliding. So, this expression can be written, or we can write this F as C into A divided by W sin psi p plus tan of phi divided by tan of psi p. Now, if this F has to be minimum, why it has to be minimum? Because in that case only we are going to get the critical depth of the tension crack. So, in that case this quantity del F del Z should be equal to 0, where this Z is what? It is the depth of the tension crack. And you can see what is Z here in this figure as well. Now, this Z can be related to the height of the slope. So, it can be related to height of the slope. What is the height of slope? It is h. So, I can write this expression as del f del z upon h to be equal to 0. Now, what happens because of the presence of this tension crack? So, the effect of tension crack will be the reduction in the contact area. Recall our discussion of the previous class. When this is not there, our contact area was from here to here. But since this tension crack occurs here, so now the contact area will get reduced to only this, that is EK. So, because of the reduction in this contact area, which we are representing here as A, what will happen to the term CA? There is going to be the reduction in the term C into A, and this would result in the reduction in the factor of safety, which we are denoting by F. You see here, if this factor reduces, it will have direct effect in reducing this F. So, it is important for us to take care of this reduced area and use this in the analysis when the tension crack is present. Now, before we go ahead, we would need to find out the weight W. So, what is this weight W is going to be? Is going to be the unit weight multiplied by the volume of the wedge that is sliding, and there is an assumption which is involved that we are taking a unit direction in the plane perpendicular to the plane of the screen. So, in order to find out the volume, I need to first find out this area, which is EFGH, and volume is going to be area EFGH into 1, because I am considering the unit dimension in the direction perpendicular to the plane of the screen. So, basically, in order to obtain this weight W, I need to first find out the area EFGK. So, let us try to find this out, that is area EFGK. This is going to be, see, I will write first as area EIJ, that means this EIJ. So, this complete area, and then I will subtract area GJK here. So, area GJK. So, from this complete area, I am removing this area. So, but I am still left with this total area. So, I have to do away with this area as well in order to get the area EFGK. So, I will have another term minus area EIF. Now, use the simple trigonometry and then try to obtain this area EIJ and see what we get. See, this expression is H, and this angle is psi P. So, we will have it half H into H cot of psi P. Similarly, GJK, this height of this triangle is H. So, I will have half Z into Z into cot of psi P. Then minus area EIF. So, this is EIF, and here for this triangle the angle psi f will come into picture. So, we will get half h into h cot of psi f. So, what we are going to get is half cot of psi p, and in bracket we will have h square minus z square and minus half h square cot of psi f. Now, weight W will be the unit weight of the rock mass which is there in this sliding block into 1, because it is the unit in the direction perpendicular to the plane of screen, and this should be multiplied by area E F G K. So, what we will get here as W is equal to half gamma h square. So, I will take h square common from this expression, and this is what that we are going to get is that cot of psi p, and I will have here 1 minus z upon h whole square minus cot of psi f, and the contact area will be what, which is represented as A. This is going to be the length E k into 1, because it is again the unit in the direction perpendicular to the plane of the screen. So, this is what you are going to get as h minus z cosec psi p, simple trigonometry E k. So, what we are doing is we are E k I can write as E k equal to E j minus j k, and you know this angle psi p, you know h, you know z, and in terms of h, z and psi p this can be written. So, I can write it again in this form which has z upon h as one of the term, 1 minus z upon h cosec psi p. So, this is how we can find out the weight of the block here and the contact area. Now, I assume that z upon h is equal to r. So, therefore, the contact area A is written as h 1 minus r cosec psi p, and weight W can be written as half gamma h square cot of psi p 1 minus r square minus cot of psi f. Now, critical depth of the tension crack we will get when this factor of safety is minimum. So, in order to make the factor of safety as minimum, we can write that del f del r to be equal to 0. Now, refer back to the expression for f, and this is what that you will get, del r of C A upon W sin of psi p plus tan of phi divided by tan of psi p, this is equal to 0. Now, you see this term is independent of r. So, its differentiation is going to be 0, and C and psi p, they are also constant. So, ultimately this equation will be reduced to del r of A upon W to be equal to 0. Now, this A and W both are the function of R, as you can see here. So, we need to do the differentiation accordingly. So, this is how that we need to do is, so what we have is del R of A upon W to be equal to 0, and what we can get from here is that is del R of A by W can be written as 1 upon W del A del R plus A del R of 1 upon W to be equal to 0. So, what we will get from here is 1 upon W del A del R minus A upon W square del W del R equal to 0. So, this is going to give me W del A del R is equal to A del W del R. Now, we have the expression of A and W with respect to R. So, we differentiate it and then we get as half gamma h square cot of psi p 1 minus r square minus cot of psi f. This is the expression for W, and del A del R. So, this is what that we are going to get is h cosec psi p into minus 1, and this would be equal to, I write the expression for A, which is h 1 minus r cosec psi p and del W del R. So, this is going to be half gamma h square, and we will get cot of psi p as it is, and 1 minus r square, and its differentiation is going to be minus 2r. This is what is the expression that we will get. So, you see here half gamma h square and half gamma h square will cancel from both the side. This h and h will go, cosec psi p, this will also go. So, we will be left with the expression like 1 minus r square cot of psi p minus cot of psi f. This will be equal to 2r cot of psi p into 1 minus r. Now, I will just further simplify this expression, and we can get this as r square cot of psi p minus 2r cot of psi p plus cot psi p minus cot psi f, and this is going to be equal to 0. Now, you see this is a quadratic equation in R. See, it is like this, like a r square plus b r plus c equal to 0. Of this form this equation is. So, how can we get the roots of this equation? You know, simply r equal to minus b plus minus square root of b square minus 4ac divided by 2a. So, we apply that, and this is how that we are going to get the expression for r as 2 cot of psi p plus minus square root of cot square psi p minus 4 cot psi p into cot psi p minus cot psi f. This whole thing will be in the square root sign. This whole divided by 2 cot of psi p. This is what that we are going to get. Now, if we try to simplify this, what we will get is this expression 2 cot psi p plus minus this 2 square root of cot of psi p and cot of psi f divided by 2 cot psi p, or this can be written as 1 plus minus square root of tan psi p cot psi f. See what will happen, this 2 cot psi p, 2 cot psi p will get cancelled out and plus minus this 2 and 2 will go, and when this goes inside the square root sign it will become square. So, 1 cot psi p will get cancelled out. So, this is what that you will be left with. Now, this r is z upon h and it cannot be more than 1. So, therefore, this positive sign here is not physically possible. So, r is going to be equal to 1 minus square root of tan psi p cot psi f. Now, since this value is going to give me minimum factor of safety, so z would be equal to z critical. So, I am going to write here the same expression as zc upon h will be 1 minus square root of tan psi p cot psi f, where what is this zc? This is the critical depth of the tension crack, or from here this zc can be written as h times 1 minus square root of tan of psi p cot psi f. So, take a note of it that this is a function of geometry of the slope and it is independent of the material properties. Keep this in mind. Now, the next step is going to be to know that where this critical tension crack will occur, that means critical location of the tension crack. So, you see here the tension crack is occurring at a distance of b from this point f. So, if we want to find out the critical location of the tension crack, that is our b will become equal to bc for z equal to zc. So, now can we define this b? So, b is going to be equal to ij minus this distance if minus gj. You see this b is going to be this distance minus this distance and minus if this distance. So, let us write that h cot psi p minus h cot psi f minus z cot psi p. So, we will get here as h minus z cot psi p minus h cot psi f. So, BC is going to be H minus ZC cot psi P minus H cot psi F. Now, we know what is the expression for ZC, just substitute it there. So, what you will get as H square root of tan psi P cot psi F into cot psi P minus H cot psi F, or we can write this BC as H square root of cot psi P cot psi F minus cot psi F. See, this cot goes inside this bracket, so it will get cancelled out with this tan psi P and you will left with only one cot term here. So, this is how you can find out the critical location of the tension crack. Now, this was all about when we have the tension crack here in this portion, that is upper portion of the slope. In case if the tension crack is developed in the slope face, that means, let us say if this is what is the situation, this is your slope face and say some discontinuity is there, and instead of having it here, now the tension crack is appearing, let us say here like this, that is on the slope face. Then what will happen? Because of this, the procedure of derivation of these expression is going to be same, except for the fact that there is going to be the modification in this weight W and the expression for the contact area. The procedure is going to be same. Now, this weight is going to be, you can derive this, I am just giving you the expression, half gamma h square 1 minus z upon h whole square cot of psi p into cot of psi p tan of psi f minus 1. So, this is how the weight W can be derived, and accordingly you can find out that what is the contact area A, and then use those expression as we did in the earlier case and obtain the critical depth of the tension crack and its location as well. Now, let us say that the tension crack which is there in the slope, now let us say the tension crack that is there in the upper portion of the slope like this as shown in this figure, and there is a presence of the water in the tension crack. Then how are we going to consider this in the analysis? So, we have it here as the consideration of the ground water table. So, in this case you are going to have the pressure because of the presence of the water and the groundwater table in the form of this U and V. So, what we have is the capital U, which is the uplift force due to water pressure on the sliding surface. And then another one we have is V, which is the force due to water pressure in the tension crack. And you can see the direction how that these two will be acting. So, what is going to be the effect of U? See, on this plane a normal force N was acting, which was some component of W earlier when the water table is not present. Now see, this U is acting in the other direction, but still it is perpendicular to this plane of discontinuity. So what will be the effect of this U is that it will result in the reduction in N, and the effect of V is going to be in two direction, because if you see that it is acting in the horizontal direction. So, it will have its component parallel and perpendicular to this discontinuity plane. So, this V will have two components. One component is going to be in the direction of sliding, and another one will be normal to sliding. Now, we need to keep in mind that all these forces are concurrent. So, this expression for factor of safety can be written as C into A, this term will remain as it is, plus you will have here as W cos of psi p minus U minus V sin psi p, this whole thing multiplied by tan phi, and this divided by W sin psi p plus V cos psi p. Now, you can substitute the expression for W, A, etc., and you know how to determine these, and therefore, you should be in a position to obtain the factor of safety under the condition when there is a presence of the groundwater table or the water is present in the tension crack. So, this is what that I wanted to discuss with you as far as the plane failure mode of the slope failure is concerned. So, we discussed about few cases of the analysis. The first case we started with the most simple one without any tension crack, simple case where there is one discontinuity plane and the rock block is sliding along that plane. The second case we took with the help of the tension crack, which can be there either on the upper portion of the slope or at the slope face. Then we saw that how due to the presence of groundwater table the factor of safety will be altered and how it can be analyzed. So, this was all about the analysis as far as plane failure is concerned. In the next class, we will take up the next failure mode, which is the wedge failure. Thank you very much.